Hi Sandhya, uh, you seem to have joined. Do you want to check your slides very quickly before we start?
How do you want to do that?
Just try sharing your slides. Just share.
Okay, I can do that.
Yeah, we still have 2 more minutes to go, so might as well check
Mm.
it quickly. Yes, could you just try changing it once?
Yeah, also let me try full screen and see if it's coming okay. Is that coming all right?
Yeah, looks fine. Yes, yeah, it's changing also
Okay.
fine. Wonderful. Yeah.
Great. So hello everyone.
Yeah.
How are you?
Good. How about you?
Hello, Sandhya. How are you?
Hi. Good, good, good. It's so nice
Good to see you.
Yeah, absolutely.
Hello, Babu. How are you?
Hello, hi. How are you? Good to see you. Haven't seen you folks in a long time.
We have not seen each other also for a very long time.
Sandhya, can you unshare your slides? So that
Yeah, sure.
people can see each other easily.
We can now see each other. In fact, I'm seeing also Babu after a very long time.
As I said, good to see both of you, and I'm sure it will be good to hear, to listen to both of you.
Yeah, absolutely. Rohini, I'm looking forward to.
Now, Sandhya, at some point, actually, I would like to chat with you on some other things. Please
Did you say something to me, Rohini?
Hello.
Can you send me your Skype at some point?
Did you say something to me?
Yeah, I did.
Oh, okay. Yeah, great. Yeah, just let me know what time is convenient. It will be really great.
So sorry for breaking this interesting conversation, but it is 8 o'clock, so I think
now we have to start. Yes.
Start. So Professor Babu, could you share your slides? Welcome everybody to this late evening session, plenary session on neutrino physics. We are going to have 3 talks in this session. Thanks for coming here at this late hour, but as we know, the number of neutrinos from the sun coming during day is the same as those that come during night. So neutrino physicists really don't care about what time it is. Anyway, thanks a lot to all the speakers for coming here. The first talk will be by Professor Babu, and he will tell us about theoretical status of neutrino physics. So Professor Babu.
Well, thank you. Hopefully you can see the slides and you can hear all right.
Just excuse me a second, just one small comment. Of course, everybody here is perhaps you're already used to it. If you have any questions during the talk, just write them on chat and we will take them once the talk is over.
All right, thank you. First, I would like to thank the organizers for the kind invitation for this exciting meeting during this difficult time. My topic is the theory status of neutrino physics. This would be a very broad overview. This is a vast area, and obviously I will be picking a few topics that I find more interesting and I have a little bit of experience in working on. So I will also outline the open questions in the field and the challenges in addressing them. As you all know, there are several other interesting neutrino sessions at this meeting. There are also overlapping sessions with cosmology and astrophysics, which also has neutrino physics discussion. There are several focus talks in these sessions. And also in this session, after my talk, there will be talks by Hirohisa and Sandhya, which will focus on the experimental side and the phenomenological side. So I want to apologize for being very selective in my topics. So let's begin with the observation of neutrino oscillations. It has been seen with solar neutrinos, atmospheric neutrinos, reactor neutrinos, and accelerator neutrinos over the last 25, 30 years. This has established that neutrinos of one flavor oscillates into another flavor. And this is only possible if neutrinos have non-zero masses. They could be very tiny, but still should be non-zero. And a simple example, as all of you have seen, is in the presence of mass, the flavor eigenstate here, mu e and mu are combinations of mass eigenstate mu1 and mu2. there is a mixing parameter that is one of the observables in neutrino oscillation. And if you propagate this electron neutrino after some time in vacuum, the probability of it looking like a muon neutrino is given by this expression. So in addition to the mixing, the flavor mixing angle for the two neutrino scenario, there is a important parameter which is the mass splitting. And if you put in numbers, this is numbers corresponding to the atmospheric neutrinos, 10 to the minus 3 electron volt squared for the mass splitting, mixing angle of order 1, length of 10 to the 3 kilometers, energy of a GeV, you see that the probability of flavor conversion is of order 1. Of course, we all know that there are, this is too simplistic. This is only for 2 neutrinos, including 3 neutrinos. There are 3 different mixing angles and 2 independent mass splittings. These have been measured, and I want to flash one slide where theorists have done a global fit to all the neutrino oscillation data. There are 2 possible scenarios. One is called the normal ordering. I'll say a little bit more about these 2 scenarios. The other one is the inverted ordering. So the parameters are the 3 mixing angles, theta 1, 2, theta 2, 3, and theta 1, 3. There is a CP violating parameter that affects oscillations. There is a single phase that appears in the oscillation probability. It's called the Dirac CP phase. Very recently, a few months ago, T2K announced their results that this CP phase cannot be 0 at the 3 sigma level. Corresponding to the normal ordering, it should lie in this range. Corresponding to the inverted ordering, it should lie in this range. And the mass splittings have been also measured. So the precision of these measurements is at the level of a few percent in most cases. So we do have an abundance of data. Of course, there are still important questions that experiments will be probing. For example, is the CP violation really there in the leptonic sector? This is one of the fundamental questions which may be related to the origin of matter asymmetry in the universe. That is still, there are some hints, and this hint suggests that there is a preference of 3 pi over 2 for the CP violating phase. This is written in a particular basis, and this is the standard parameterization of the neutrino mixing matrix, analogous to the Kawibo-Kobayashi-Maskawa mixing matrix. Okay, so we do have this information. This is all developments over the last 25 years. Okay. We would like to, the theory of neutrinos will attempt to explain these observations. Okay. So let's do the first simple thing. We can compare what we know from the neutrino physics to what we know from the charge fermions. So here is a plot of different charge fermion masses on a logarithmic log scale. You see that among the quarks of different generations, there is a huge hierarchy of order 5 orders of magnitude. And similarly in the down-type quarks and charge leptons. But if you look at the neutrino masses, they are not so strongly hierarchical. All the oscillation data could be fit with a neutrino mass hierarchy spanning within 1 order of magnitude. For example, here you see 10 to the minus 5 electron volt squared. That is the splitting square. So if you take the square root of that value in the normal hierarchy, that would be indicative of one of the neutrino masses. And then if you compare it with the square root of this one, it's only a factor of 10, factor 7, and factor 8. This is very different compared to the 5 orders of magnitude hierarchy that we see in most other charts. So neutrinos seem to be a little bit different compared to all the other fermions that exist in nature. If you look at the mixing among the flavor mixing among the leptonic sector, you have the leptonic mixing angles. This is again determined from neutrino oscillations with the accuracy of 10% or so, except perhaps the atmospheric neutron. There is still some uncertainty that we still don't know. It appears to be close to 45 degrees, but one of the important questions for future experiments is to see whether it is a little bit below 45 degrees or above 45 degrees, and which quadrant the atmospheric neutrino mixing angle lies. But you see that if you compare it with the quark mixing analog, which is VCB, the second and third generation mixing in the quark sector, you see this is about a 1, whereas the quark mixing is quite small, 4% versus almost 100%. Here is the CKM mixing parameters are approximately 1 along the diagonal and very small along the off diagonal, that is shown here. Whereas in the neutrino sector, the off diagonal entries seem to be comparable to the diagonal. The θ13, this is the reactor neutrino mixing angle, approximately 0.16. That is the smallest entry, but it is still, it could be, it's almost comparable to the Cabibbo one, right? So we would, on the theory side, I think it is an important question to understand these features. Neutrino oscillations are providing us a great deal of information on the flavor structure. And ideally, we would like to put these observations in the quark sector and the electronic sector together into some bigger picture. I'll talk a little bit about attempts to do so. There has been quite a bit of attempts to try to unify these quark masses and lepton masses along with the small quark mixing and large lepton mixing. So this is, I think it has been the basic questions in neutrino physics for past several years. We would like to understand answers to all these questions. Are neutrinos their own antiparticles? This is not determined by the neutrino oscillation. The neutrino oscillation data that I showed works equally well when neutrinos are Dirac particles or when they are Majorana particles, which is what I mean by their own antiparticles. So different types of experiments need to be performed to determine whether neutrinos are Majorana or Dirac. And the most promising way of doing that is through Neutrinoless double beta decay searches. And I will say a little bit about it. And I already talked about CP violation in neutrino oscillation. If CP violation is established at a convincing level, like 5 sigma, which is one of the goals of forthcoming facilities, such as Dune, Hypercamia, etc. Then this will be, it'll add to our fundamental understanding of how nature works, but it may be also closely related to the baryon asymmetry. Is the neutrino mass hierarchy normal or inverted? I mentioned that. I will say a little bit again more about what the difference is. The oscillations are not sensitive to a certain sign. Remember that in the 2-flavor oscillation formula, it is the sine squared of this delta m squared that appears. Okay, so if you change the sign of the mass splitting, the oscillation formula in vacuum remains invariant. Therefore, it allows for the possibility that this delta m squared could have positive sign or negative sign. Now, in the case of 2 of the flavors, sign is determined by the delta m squared between 2 and 1. It is fixed. It is because the solar neutrinos undergo MSW resonance inside the solar core. So because of that, that only happens if this delta m squared 2-1 has a particular sign. Whereas the atmospheric neutrino oscillation, which controls the delta m squared 3-1, it is allowed to be either positive or negative. That determines the neutrino mass ordering. And this is one of the fundamental questions that in the near future we hope to be able to understand. So that is in my list of questions: is the mass hierarchy normal or inverted? Are there light sterile neutrinos? This is a question because of certain various anomalies that have been observed in short baseline neutrino experiments, starting from the LSND experiment some 25 years ago. It has been kind of supported by the mini boon experimental data. So that would require a neutrino species having a mass of order electron volt, and that does not fit the 3 neutrino oscillation scheme. So the question, an important question, is the other additional neutrino existing in the universe. And if such neutrinos do exist from collider physics, from Z boson properties, that can, these additional neutrinos cannot couple to the Z boson. in any significant way, so they must be sterile. So these are the questions that I think the experimental efforts in the next few years will hopefully settle all these questions. But I have an even more ambitious question. We would also like to know what's the scale of the neutrino mass generation. Current data can be accommodated in theoretical frameworks when the scale of neutrino mass generation is near the grand unification scale, 10 to the 14 GeV. You can also explain it by making it a Dirac neutrino with the scale of mass generation is the sub-electron volt. So there is a huge span of energy scale over which neutrino mass generation could have occurred. We would like to understand that. Simply studying neutrino oscillations probably is not enough to get an answer to this question, but there are correlations. For example, if LSC is a heavy neutrino, by studying its property, we might be able to learn more about. We have to be lucky, but we might be able to learn more about the scale of neutrino mass generation. Or if neutrinoless double beta decay is measured and it prefers certain pattern of neutrino mass ordering, and if the neutrino oscillation experiments prefer a different pattern of mass ordering, that means that there is something non-standard outside of a neutrino mass that is involved in the neutrino mass generation. What explains the pattern of neutrino mixings? I showed the pattern. Now we need to understand that at a deeper level. Yeah, there are some flavor symmetries that are playing important role in generating these last mixings in the neutrino sector. Can neutrinos be unified with quarks? That's of course an ambitious question. That would be, of course, really nice. And is the neutrinos equivalation related to the baryon asymmetry of the universe? I list these. These are important theoretical questions, but we may not have answers to these questions. If we will be lucky if we are able to answer some of these questions. But these the first four questions are more practical. It would be hopefully be addressed in the next decade or so. Okay, the mass ordering, I had already mentioned that the delta m squared 3.1 have two possible signs, which is currently unknown. In the normal hierarchy, which is on the left side, electron neutrino is mostly in the lightest mass eigenstate. In the inverted hierarchy, electron neutrino is mostly in the heavier eigenstate. The heavier eigenstates are nearly degenerate. So this is something that could be tested in forthcoming experiments such as Juno, Dune, Hyper-K. And I also want to highlight the contributions INO could make in neutrino oscillation in one of these fundamental open questions in neutrino physics, which is the mass hierarchy. I should also say that I will speak a little bit about high-scale theories which generate neutrino masses and mixing, the grand unified theories, and they tend to prefer this normal ordering. If experimental efforts show that, such as from INO or Dune or Hyper-K, if we see that the mass ordering is of the inverted type, it actually is saying something very deep. That would say that neutrinos are really distinct from quarks and leptons. They are probably not even unified with quarks and leptons, because in the quark sector and in the charged lepton sector, the pattern appears to be more like the normal ordering, that is the mixing between nearest neighbors in the quark sector is bigger compared to the mixing between, say, the first family and the third family. So this would be a very important question that would be addressed in the coming years. Now, about the nature of the neutrino mass, is it Dirac or Majorana? Oscillations cannot tell us that difference. However, neutrinoless double beta decay will help address this question. And the process is nuclear decay with the emission of two neutrinos with no, this is a double beta decay without any neutrino emission. And this goes through this diagram through W exchange, and the light neutrino is being exchanged. And this can only occur if the neutrino has a Majorana mass, because lepton number is violated. You have two final state electrons, which carry lepton number of 2 units. This has been studied, and again, this prediction for this effective mass, the double beta decay mass, is given by this. So the unknowns here are these so-called Majorana phase. These are Majorana phases that do not appear in the oscillation formula. So these one can vary them because they are phases. If you vary them, you get certain ranges. And as a function of the lightest neutrino mass, this is shown here. If the neutrino mass spectrum is inverted, it could be, this is relatively large. The current limit from, say, the best limit, one of the best limit comes from Kamla and Zen experiment on neutrinoless double beta decay. Its effective mass limit is about 0.2 electron volt. So it is getting there to close to being probing the inverted hierarchy spectrum. So that's very exciting. If it turns out to be a normal hierarchy, one has to wait for next generation of experiments because the effective mass is then much smaller. Of course, there is a third region where the two merge together. This is called the quasi-degenerate neutrino, where all three neutrinos are very close in mass, but then there are small splittings to explain the neutrino oscillation. Okay, so now the best understanding that we have of neutrino, smallness of neutrino mass is through the seesaw mechanism. The seesaw mechanism assumes that there is a right-handed neutrino. Here it is written as nu c, so that it is left-handed, and it mixes with the standard like normal neutrino through this mixing matrix. And if you diagonalize this, in the assumption that the right-handed neutrino mass, which is the Majorana mass, by the way, it is much heavier than the Dirac mass. The Dirac mass is comparable to, it breaks the electroweak symmetry just like the top quark mass does or the electron mass does. We don't know exactly what the Dirac mass is because if you try to learn something from the charged fermion sector, we have the Dirac mass of the electron is a half MeV, whereas the Dirac mass of our top quark is 174 GeV. So there is about 5 orders of magnitude difference. And the light neutrino mass goes like the Dirac mass squared of the right-hand neutrino mass. Okay, so roughly the square root of the atmospheric neutrino mass splitting gives the mass scale for light neutrino, which is 0.05 electron volts. We can get that by assuming the Dirac mass to be 100 GeV and the right-handed neutrino mass to be near the gut scale, 10 to the 14 GeV. That's a possibility. But we could equally have, say, Dirac mass to be MeV, similar to, say, electron mass, and right-hand neutrino mass to be at a TeV scale. Then you, again, with this formula, you get the electron or sub-electron volt neutrino. What happens is that this right-handed neutrino being a complete singlet of the standard model, it has no interaction, it has a bare mass, so we can integrate it out. Once we integrate it out, we get an effective Lagrangian, which is not renormalizable, but it has 2 lepton fields and 2 Higgs fields. And once we give the Higgs field a vacuum expectation value, this is what you get, the md squared over the heavy mass. Now, in the context of Seesaw, this heavy mass scale lambda is identified as the right-handed neutrino. Now, some people may take this to mean that, well, we can accommodate everything that needs to be accommodated in the neutrino sector by writing an effective operator, and that effective mass scale could be 10 to the 14 GeV. So that is it. So we are done. We can fit anything that is observed in neutrino oscillation. Technically, that is correct. We could have such a high scale of symmetry of neutrino mass generation, and we are probing the Wilson coefficient of this operator. However, I think we are more ambitious. We want to open up. We want to look deeper. I think there's a saying that if you look deeper, you're likely to find something new. This is true for obviously in the experimental situation, but I would say that it's also true for theory. If you see this effective operator, I think we should not stop there. It's like a Fermi theory of weak interaction. We are not happy with the Fermi theory. We want to go deeper and find the W boson and the Z boson. In the same way, we want to see what caused this operator. We want to see it coming from the right-handed neutrino, or we want to see whatever causes, say, type 2 seesaw mechanism. Indeed, if you open this operator, you see new phenomena. And one of the new phenomena that appears to open this up is the possibility that the right-handed neutrino in their decay can cause baryon asymmetry through the mechanism called leptogenesis. Leptogenesis, if you try to do leptogenesis with the reflective operator, you would not actually see this. So it is important to probe the origin of neutrino mass. Okay. And there are a variety of seesaw mechanisms. I will briefly mention that. This is the effective operator, and you can get it by integrating out a fermion, and that is called the type 1 seesaw mechanism. We can also integrate our fermions belonging to SU2 triplets. That is called the type 3 seesaw mechanism. And we can integrate out a Higgs triplet. This is a Higgs triplet. And once you remove it from the low energy theory, we get this effective operator. That is called type 2 seesaw. And this Higgs triplet has the property that it contains in it a scalar with a charge of +2. And experimentally, one can look for this double charged scalar. It will decay, it can potentially decay dominantly into same sign dilepton. So this discovery of a same sign dilepton may provide us some hint to the origin of neutrino mass. If we don't know which one is the right theory, it is an experimental question, but we should probe our possibilities. There's another mechanism, again, belonging to the seesaw. It goes by the name inverse seesaw. Here one introduces, in addition to the right-handed neutrino, a wild fermion, two-component wild fermion, N. And so that the neutrino mass matrix has this form, where this N has a small mass, mu. And now if you do the seesaw mechanism, you get a more complicated expression. But the main point is that the smallness of neutrino mass now can be explained in terms of the smallness of this mu parameter. Okay, so this will allow possibility of a low-scale neutrino mass. Now, there is a deeper origin for this. I think when Mohapatra and company initially talked about this kind of a setup, they were motivated by higher unified symmetries, such as E6. E6 does automatically contain an additional wild fermion, which can potentially give this kind of a structure. Now, the lepton number violation is an important question related to the neutrino mass generation. But in this setup, it's not so easy to observe lepton number violation, because if this mu is small in order to explain smallness of the neutrino mass, and the way if mu is set to 0, lepton number remains unbroken in this system. Although there are various attempts to look for this type, the inverse seesaw at colliders. I listed some of the original papers on this study here. Okay, coming to experimental test of type 1 seesaw. Type 1, we saw, well, if we simply state seesaw, most people take it to mean type 1 seesaw. So that's the most more talked about mechanism. Part of the reason is because it is probably the simplest way. And secondly, it also comes out automatically in simple unified theories such as SO10. And I will have a little bit more to say about that. Now, this right-hand neutrino is a new ingredient. Now, it could be very heavy, but it could be also light at the TeV scale. So let's entertain the possibility that this right-handed neutrino is near the TeV scale. It's difficult to test with such a TeV scale right-handed neutrino, because to produce them, it has no interaction with the gauge growth, right? Except through its mixing with neutrinos. But the mixing of these singlet neutrino with a normal neutrino has to be, it is highly constrained. These constraints come from a variety of experimental observations. First of all, if that mixing is between the active and this sterile neutrino, the heavy sterile neutrino, if it is large, it will contribute too much to the neutrino mass. It might contribute too much to lepton number violations, such as the Neutrinoless double beta decay amplitude. There are charged lepton flavor violation mediated by this object. Lepton universality may be affected. There are also experimental limits on direct search for N. So if we try to test Seesaw at the TeV scale, we have to satisfy all these constraints. There are simple ways of avoiding many of the constraints, and I list here something that was noticed. Well, it is known to people who have worked in neutrino mass models. Tatavada Ghosh and I pointed out this possibility that if you use some specific form of the Dirac mass and the Majorana mass, the effective light neutrino mass matrix contribution becomes 0. And in this limit, what happens? It's the light neutrino mass contribution becomes 0 because there is an approximate lepton number symmetry. You can assign the lepton numbers for these 3 right-handed neutrinos like this, and you see that there is no Majorana mass allowed for neutrinos. However, in this setup, discovery of lepton number violation, such as producing this right-handed neutrino and its subsequent decay into to produce 2 same sign leptons and jets, those processes will be suppressed because of this unbroken approximate lepton number. Okay, let me move on to theories of neutrino masses based on unified symmetries. These are more ambitious because they attempt to unify the mixings and masses of quarks with leptons. And as I showed in the very beginning, they are not parallel to each other. So here is a quick motivation for grand unified theories. It explains the electric charge quantization, which is known to high precision in atomic physics. The cancellation of anomalies that is seen in the standard model is automatic in many of the grand unified theories because the starting point is anomaly free. We can have a better understanding of the quark and lepton quantum numbers. Importantly, these models predict existence of right-handed neutrino. And because of that, it predicts the seesaw mechanism. There is unification of couplings, beta unification, possibility of baryon number violation while leptogenesis. These are the main motivations. The gauge coupling unification, as if we extrapolate the couplings in the standard model, they tend to unify, but they don't quite meet at one point. However, if you have low energy supersymmetry, this is one of the great features of supersymmetry is that it predicts correctly unification of the 3 gauge coupling. Now, these days, supersymmetry is under tension. We have not seen it at the colliders. So, but unification does not really rely very much on supersymmetry. It can exist without supersymmetry. For example, in SO10 unified theory, there could be a Pachi-Salam intermediate scale. Then the unification occurs. There has been a great number of papers written on this topic. And I show here how unification works. This is on the left side is unification with Pachi-Salam with explicit left-right parity. On the right side is without left-right parity. So this can happen in SO10 unified theories. And here is a good way of organizing the particles into a spinor representation of SO10, or all the fermions, quarks and leptons, including the right-handed neutrino, arise from the same multiplet. And there is a very nice way of understanding the electric charges, or the hypercharge, which in turn leads to electric charge. The first 3 quantum numbers are for color, and the last 2 are the spin, and the hypercharge is a linear combination. So it elegantly explains the quantum numbers. So in the simplest of these models, SO10 models, the Yukawa coupling can come from Higgs belonging to a 10 so fundamental Higgs, and this is the 126 Higgs. This model turns out to be a predictive framework for neutrino mass, because one can write down there are only 2 Yukawa couplings. These are symmetric Yukawa couplings. From there, we can write up mass matrix, down matrix, Dirac matrix, charge lepton matrix. Therefore, we can compute the neutrino mass spectrum in terms of the charged fermion mass. There has been a significant amount of industry in trying to understand the neutrino spectrum within this so-called minimal SO10 theory. I think this is a result from paper I wrote with Machisano well before the Diabe result came. This is a distribution of sine squared 2 theta 1 3. And this is the p violating phase in this context. And you see this sine squared 2 theta 1 3 was peaking within the model parameters around 0.08. And that very nicely agreed with the experimental measurement at DAE-BRNS. This did not have to be, but these models do predict large. It couldn't exist without large reactive neutrinos. Here is the fit again prior to DAE-BRNS from Joshipura and Patel. If you look at the global fit within this model, you see that it has a very good chi-squared. This is from the type 1 seesaw mechanism. And again, sine squared 2 theta 1 3 was, this is sine squared theta 1 3, was precisely consistent with the subsequent measurement. It turns out that type 2 is not a good fit within this version. So we have actually, this is an updated version of this fit. This is my collaborator, my student Saab did this fit for SUSY and non-SUSY. It still gives an excellent fit to all the observation. Now that we have some information of the CKM phase, we have also, sorry, not the CKM, the PMNS phase. We have also included that into the fit. It is possible that it is consistent with this model. So this is, I mean, if you think about it, we had, don't think I mentioned it, but there are 11 parameters. We have about 19 observables, including the quark masses. And then there are 7 phases, but the 7 phases are not complete full parameters, but because when they vary, when you vary the phases, you don't get you don't get a lot of freedom in doing that. So this is, I think it is a nice fit. I think I should speed up a little bit. So can we pin down the CP phase in this context? And the answer is not so easy because there are multiple chi-squared minimum when we marginalize on the other parameters. This is what we found. So the preferred value, there is a minimum here in chi-squared, but there is a minimum somewhere else. So it's it primarily accommodates the observed CP validating phase. Now, recently in this work, in a recent work, we have also tried to explain the mass hierarchy based on a clockwork. Clockwork is a new idea that has been that was suggested initially to explain the gauge hierarchy by these people, but it has been used to explain the fermion mass hierarchy. The basic idea is that you introduce a set of vector-like fermions that mix with the standard model fermion. And this, the standard model fermion, because it is chiral, it will be a 0 more of this, a chain of mixing. And small numbers arise naturally in this context. So here is an example for this minimal SO10 embedded into a clockwork. Here is the standard model fermion. It is coupled to some chain of vector-like fermion and a second chain of vector-like fermions. And these are going to provide the small numbers that are needed to explain the mass hierarchy. And yeah, here is the exact fit, like it's the best fit value for this minimal SO10 clockwork model. And there are 2 parameters, epsilon1 and epsilon2. These are explained by this chain of clockwork. And there are only, see, all the coefficients are of order 1. Okay. These unification ideas can be tested in Nucleon decay. So it's, let me go to the prediction for Nucleon decay. These models predict that the lifetime to E plus 50 to be less than about 10 to the 35 years. The prediction itself has some large uncertainty, but the branching ratios are well predicted in this model because it has to do with the flavor factor. Okay, the last, let me see if I have a few, 3 minutes. Okay. Last few minutes, I will explain the idea of radiative neutrino mass generation. It is the idea that neutrino masses are induced through radiative production, loops like this. Okay, that can explain the smallness of neutrino mass. The simplest such example is the Z model, and the Z model is, okay, let me, yeah, it is where you extend the scalar sector and you get neutrino mass with an interesting flavor structure. And since there are some loop suppression and chiral suppression proportional to the, say, electron mass, the new physics could be at the low scale. And I will skip the fit to the neutrino and then come to the last point, which is non-standard neutrino interaction. These are effective interactions neutrinos could have with matter, which is generally parameterized in this way in terms of this epsilon. The one here is the Wolfenstein term, the weak interaction term. Others are all new physics terms. And even a tiny bit of, say, 1% of non-standard epsilon mu tau from ice cube. See, the probability distribution for oscillation becomes very different. This is for 0 NSI versus 1% NSI. So the epsilon mu tau from ice cube has been highly constrained at the level of 10 to the -3. The Z model actually gives a large contribution to non-standard interaction. These are the diagrams which by which this has been studied by our group recently, and including various constraints. We find that within the model, we have to take into account flavor violation constraint, LSC constraint. We found that the Chask-Hicks mass of about 100 GeV is permitted. And that leads to non-standard interactions of this epsilon, the diagonal epsilons of about a few percent, especially for epsilon tau tau. Okay, I think I'm going to skip the last one. Come to the conclusion. A variety of seesaw mechanisms exist. They're all interesting. I've talked about class of guts, which with some predictivity. In many of the cases, new particles are predicted at the TeV scale, especially in the context of radiative neutrino mass generation. The non-standard interactions are interesting way of testing the 3-neutrino oscillation paradigm. I did not talk about the zeros in the neutrino mass. That's another exciting way of understanding flavor structure. So neutrino CP violation, double beta decay, mass hierarchy measurement, understanding all these will greatly enhance fundamental understanding of the nature. And I think I hope INO will play a major important role in our understanding of these. Thank you.
Thank you, Professor Babu, for that very comprehensive review of neutrino theory. Any questions? Please type in the chat box or raise your hands. Yes, Ashish, you can unmute yourself and ask your question.
Sorry, so I am Devasis. Somehow the name is different. So I have kind of a naive question. So as we know that neutrinos interact only weakly. So can one talk about using them as a probe for neutron star mergers, like the LIGO experiment did with gravitational waves? So can one use neutrinos to probe that? Like, do you expect a neutrino star merging will emit neutrinos or something like that? So that was my question.
Yeah, I think there are more. I'm not an expert on this, but I think neutrino stars with the standard interactions are not stable. Of course, neutrinos have a strong impact on neutron, the supernovae. So we can learn quite a bit about neutrino properties by the observation of neutrino signal from supernova. As far as stable, the neutron stars in the core collapse supernovae, neutrino get trapped, and in the last phase, they carry most of the energy of the supernova, right? So just from that property, we know that neutrino mass cannot exceed several tens of electron volts. And future supernova neutrino observation could help even understand the ordering of the neutrino mass. But as far as a stable neutrino stars, unless there are some very exotic interactions, that would be very unlikely.
Rohini, you can go ahead with your question.
Thank you.
Okay, thank you, Amol. I just had a very, maybe you went by too fast there, but I think you said that in some model, a charge scalar of 100 GeV is still allowed. It's
Yes.
possible. Now, such a charge scalar in these models does it not decay with, does it not couple with the B quarks and cause problems in the B decays?
Yeah, so in this particular model, this is this specific to the Z model of neutrino mass generation. There is an additional Higgs doublet. It could have couplings to quarks, but it did not. The neutrino mass does not depend on whether it has a coupling to quarks or not.
Okay, so you will dial it to 0 or low.
Yeah, so this is entire. This analysis is done assuming that the couplings to quarks of the additional Higgs doublet is tiny. Otherwise, it causes a flavor violation in the.
That's exactly what I asked. The B, that's exactly why I asked.
Yeah, it does. It would cause problems, but in the if it's primarily coupled to leptons, then we easily avoid that.
So you're just dialing that down. Okay.
Yes. Yeah. Well, it's these are free parameters, so this is
so that's fine.
These are the optimum, the biggest signal one can get in this model.
Okay. Thank you.
Let's take a last question from Sandhya.
Okay, so I had this question on slide 12 when you were talking about inverse seesaw. You said because mu is very small, which was the lepton number breaking parameter in the inverse seesaw framework. Because mu is very small, it's difficult to see lepton number violation in this class of models. But isn't it true that, all observations which can actually give us lepton number, signature of lepton number violation are anyway suppressed by the neutrino mass. So like generally, in this case,
I think that is.
Yeah.
Yeah. So yeah, to see lepton number violation at colliders, it is, in my opinion, it is very challenging. It's because once you see lepton number at the collider, typically that creates whatever that reaction is. You can close it and get neutrino mass. Okay, a Majorana mass to the neutrino. And in the same way, if it is coupling, if the observation involves the electron sector, then you also get too much of neutrinoless double beta decay from that observation. So I think so type 2 seesaw is a good example. If you produce as double charge scalar, and if you see them decay to same sign dilepton, that doesn't mean that lepton number is violated. You must see in two different modes. One is the type double charge decays into same sign dilepton, and then one should also see that it is decaying to 2 Ws. But when you try to put that parameter space where both coexist, that is almost not there, or the number of events become very tiny. So it is very challenging in type 2 seesaw or in the inverse seesaw to see signals of lepton number violation. And I think lepton flavor violation is much easier to see than lepton number violation.
So that was my point, that you might have signatures of these models in other channels, but whenever you talk of exactly looking at lepton number violating channels, mostly it's the neutrino mass.
The neutrino mass and neutrinoless double beta decay become
it's very small. Okay, thank you.
So thanks a lot, Professor Babu. Any more questions you have for him could be sent to Slack, and then we could try to contact him. And
I will stop sharing my screen.
Can I make a comment, please?
Okay, quick comment, yes.
Yeah, this is with respect to the CKM matrix in the quark sector and the PMNS matrix in the leptonic sector. Their structures are very different. The CKM matrix is a very interesting structure as pointed out by Wolfenstein long ago. Namely, the theta 1,2 element is of order lambda, and theta 2,3 element is of order lambda square, and theta 3,1 is of order lambda cube. And that is in agreement with the facts mostly. Whereas in neutrino sector, we know this is not true. It's completely different. Now, the suggestion which we have made is that the same Wolfenstein ansatz works for neutrino also, if you recognize that this might be at a very high scale, and then you have to run down using enormous group, and because of the quasi-degeneracy of the neutrino masses, the mixing angle neutrino sector get enhanced, and you can get exactly what is observed. So the Wolfenstein structure is valid for neutrinos also. That is the point. And that makes the Wolfenstein structure very important to understand. As far as I know, there is still no understanding. An empirical suggestion made by Wolfenstein long ago, and it agrees. But now my point is that the importance is doubled up because we can explain even the leptonic sector by Wolfenstein structure. That's all I wanted to say. I mean, is Babu, I mean, can Babu make a comment on this, please?
Yeah, thank you. I think that's a very interesting point. I actually did not discuss the renormalization group evolution. There could be significant changes in going from one scale to the other, but by comparing at low scales, they look quite different.
Oh, yeah.
There have been attempts to, yeah, as you say, there are these renormalization group ways of understanding the hierarchy in the mixing matrix. But there is also a separate way of starting from something called a tri-bimaximal mixing. And then the starting point, the zero, so in the case of CKM matrix, you start from an identity. Wolfenstein assumes that to begin with, it is an identity. Then there are small perturbations. So one could do similar things for the neutrino PMNS matrix by starting with, say, tri-bimaximal. In that limit, the theta 1,3 would be small. And then people have tried to expand around the tri-bimaximal mixing. That's a possibility. But again, in that case, the starting points are quite different between quarks and lepton. Thank you.
Thank you.
Thanks a lot. I think we will now go to the next speaker, going to be Professor Hirohisa Tanaka. Tanaka-san, can you share your slides? Yes. Yes, please, you may start.
Okay, can you hear me?
Yes.
Hi, my name is Hirohisa Tanaka. I'm from Slackman Stanford University. Thank you very much for this opportunity to present a snapshot on experimental neutrino physics. And I thank you, Professor Babu, for the excellent introduction to the theory and physics behind much of what I'm about to talk about, which I'm certainly will profit from. So as you know, it's already been 5 years since the Nobel Prizes are awarded in, for the discovery of neutrino oscillations, and more than 20 years since its discovery in atmospheric oscillations. But I think the implications of this are enormous, and we still have decades to go to fully understand these things, as Professor Babu noted in his theory talk. And so in what follows, I will follow developments related mainly to the study of neutrino mass. Now, the space of neutrino physics is enormous. And so you can imagine if you start over here, there's the questions of the origins of neutrino mass and what is it and where does it come from. There's experimental study that probe its parameters and mixing, but then we can also use neutrinos to probe things like nucleons in the nucleus, or even the Earth, or even the sun. And then as we look further out into the universe, the neutrinos become messengers that tell us about astrophysical processes which are happening very, very far away. And then once again, the fundamental properties of neutrinos come back to tell us about how they impacted the early universe, whether it's the formation of structure, the CMB, or even questions like why the universe is matter dominated and to some extent exists at all. And so in my talk, I will sort of focus mainly on sort of the top left part of this related to the question experimental probing on neutrino mass and neutrino mixing. The situation sort of reminds me of sort of every year I plan to make a visit to India, and I ask myself, where should I go? And I realized that 1 week is certainly not enough, and possibly 3 weeks is not even enough to make a reasonable trip. And it probably takes 1 month of research just to make a list of things to do that are important, that I could prioritize. And so I usually just give up and I never manage to make this trip because it's just too much to think about. Okay, so in terms of the neutrino mass and mixing, there's just a brief summary of Professor Babu's talk that we know that neutrinos, that there are 3 flavor eigenstates, and then there are the electron, muon, and tau neutrinos, but likewise the neutrinos come in 3 mass eigenstates, which we typically number by nu1, nu2, and nu3. And then we also know that these flavor states, eigenstates mix, so that that one is a linear combination, a unitary linear combination of the other, as shown by the equation over here. And therefore, if we start with a given flavor state, the time evolution with quantum mechanics allows different neutrino flavor components to arise in the wave function. And this gives rise to things like what we call neutrino oscillations, which is a time variance of the flavor content of the neutrino as it moves along, particularly in this parameter L over E, which is the distance the neutrino travels divided by its energy, which is effectively sort of the proper time that the neutrino experiences through its propagation. And so if we look at, for example, the neutrino oscillation probability in vacuum, the probability that a neutrino of flavor alpha becomes probability of flavor beta later, we see that the amplitudes of these oscillations are governed by the mixing matrix. So this unitary relation between the mass and the flavor eigenstates. But then the wavelength in terms of this L over E is determined by the mass squared splitting. So how far split the mass eigenvalues are. So if we specialize to the case of 3 neutrinos, we have sort of this standard parameterization, which as we saw in the previous talk, can be parameterized by 3 mixing angles and also a complex phase. And there might be additional phases if the neutrino chooses to be a Majorana particle. And we also know from the current experiments that the mass splittings have sort of 2 scales. There's one at around 2.5 times 10 to the minus 3 eV squared, which suggests that the first maximum of the neutrino oscillations will happen at around 500 kilometers per GeV. And then we have the solar mass splitting about 30 times smaller, 7.8 times 10 to the minus 5 eV squared. And then we also know that, the mixing is very large. So basically every parameter in this mixing matrix is large, with the smallest one being this upper right quadrant, which is still relatively large, as Professor Babu mentioned, at the scale of the Kabibel angle in the quark mixing. So I'd like to start by trying to directly address the issue of neutrino mass. And indeed, there is a way to kinematically probe neutrino mass, which is to look at the decay of an isotope like tritium by its beta decay, and looking at basically the endpoint of this spectrum from electrons. And so if the neutrino were to have a slight mass, then it must take some of the energy from this decay, and therefore the endpoint of this electron spectrum will fall off more quickly than we expect if the neutrino were massless, and that's what's shown here on the bottom right plot. But given what we know about the neutrino masses, this is a very, very subtle effect, and so the vast majority of the spectrum is unaffected, and basically we're looking at something like 1 part in less than 1 trillion of the decays occurring in the relevant endpoint where we could be sensitive to the neutrino mass. So it's very clear from this that you need an extremely intense source, and also to have very precise kinematic resolution on an electron to probe this this very subtle effect that would arise from the neutrino mass. And so this year we heard some very exciting results from the Katrin experiment, which is one such experiment, which basically uses what we call the MAC-E filter technique, where a very intense source of tritium is introduced. The electrons are channeled along this direction, and then basically this big thing here introduces a electrostatic potential, which blocks electrons up to a certain energy. And so by scanning that potential, we're basically able to probe how many events lie along each part of this spectrum. So it's been already more than 10 years ago that this enormous spectrometer made its way across Germany to Karlsruhe, to where it is now. There were some challenges with the tritium source, but now the experiment is running very well. And so here you can sort of see the data that's been taken. And so what's been publicly shown so far is the data taken about 2 years ago in 2018 in what they call the first campaign. And so these are the results that they have here on the spectrum. And so this is, just to be clear, that the statistical errors here are blown up by a factor of 50 to illustrate just how precise this measurement is. And then based on that, they are, so far not seeing any evidence of a neutrino mass and obtaining limits of the order of electron volt. We expect much more for Katrin. This is just the first results from their first year of operation. They already have quite a bit more data, I think about 5 times more data already in the can. And so we can expect results from that soon. And then there's a third campaign going on where they will further increase their data. And so as was mentioned previously, we're definitely getting into the sub-EV region and starting to probe approach the region where the neutrino mass, from what we know, which is a minimum of 15 millielectron volts, should start to be, may start to make its presence felt. But yeah, we'll have to see. So as Katrin continues, there are additional, well, there are new ideas for how to make this kind of measurement. Some of them using the cyclotron radiation from beta electrons by orbiting them in a magnetic field. So that's sort of an alternative way to this MAC-E filter to measure the electron momentum. Then there's also this technique of using electron capture in polonium, where we're basically a different process where the neutrino mass will also impact the kinematics of this process. So these are this is a very exciting area where we expect a lot of progress over the next decades. So there was the question of the nature of neutrino mass. And as we saw, there's the possibility that neutrinos may be unique in the standard model and the possibility of being its own antiparticle. And so there is a process that we know called... yeah, there's a process called double beta decay, where basically we have two neutrons within the nucleus simultaneously undergo beta decay. And sometimes this is kinematically allowed for certain nuclei. Now, if the neutrino is in fact its own antiparticle, it's also possible for the neutrinos that are emitted in this beta decay to effectively annihilate each other, and resulting in a process which is kinematically constrained to give 2 electrons with a total energy at the endpoint of this decay process. And so the challenge of this experiment is to first have enough of this special isotope which can undergo this double beta decay, and then to see and isolate a component of this decay which is occurring precisely at the endpoint of the spectrum. And so the observation of an excess here would indicate that the neutrinos are in fact Majorana particles. So this is a very exciting experimental area, because there are just so many different techniques that are underway here. I can't summarize them all, but basically there are different optimizations that people are making. On the one hand, we are trying to separate the normal beta decay, double beta decay, from the neutrinos double beta decay. So energy resolution is clearly important in order to separate this endpoint from the rest of the decays. There are backgrounds, so background rejection is also important. And then finally, we are into the era where we're probing lifetimes that are over 10 to the 26 years. So scalability is also very important. If you want to be sensitive to this process, you must be able to accumulate enough isotopes to basically have a chance of seeing this decay. And that also comes back to the choice of the isotope that you use. Generally, experimentally, you would favor to have a higher energy so that backgrounds are less of an issue. But then there are also questions of the natural isotopic abundance of the isotope that you're after. If it's very small, then you may require some complicated and expensive enrichment techniques to extract the isotope that you want. And so, as you can see, for various isotopes, it's a very competitive area where experiments are reaching lifetimes limits of on the order of 10 to the 26 years. So just to give you an idea of an experiment, so previously we saw the experiment from Gerda, and so here you have the double beta decay spectrum, and then within here one expects to see the neutrinoless double beta decay. And so this is an experiment which is really optimized towards energy resolution. Another optimization is shown here, where from the Kamlan-Zen experiment, where we have a very large volume of liquid xenon dissolved into simulator. And so here we are sort of targeting mass and background rejection through self-shielding. And then so the potential neutrinoless double beta decay signature would appear here if it were present. So as we saw in the previous talk, there is sort of a natural next target we related to this inverted hierarchy, where there is a lower limit basically to the decay rate if the neutrinos are in fact Majorana. And so experiments like Kamlan-Zen and others are starting to approach this region. And so the next generation experiments like Nexo or Snow Plus or subsequent upgrades of Kamlan-Zen or Cupid are targeting to basically get through the inverted hierarchy and have a definitive sensitivity if the neutrinos are in fact inverted and also Majorana. And so beyond that, we can think about the enormous challenges of trying to probe some of this additional space that would remain if neutrinos were, in fact, in the normal ordering. So let me move on to neutrino oscillation experiments. And so as we've seen, the reactor experiments like DAE, double show amino, have given us very precise measurements of sine squared theta 1,3. I would say this program has matured and is sort of reaching a sunset period and has a just incredible legacy of giving us the most precise measurement of any of the neutrino mixing parameters. And so there is sort of a successor to this program in the form of Juno, which is also using a nuclear reactor, or many nuclear reactors at a different baseline, where we're actually sensitive to oscillations of both the atmospheric scale and the solar scale. And there's a possibility of both measuring the sine squared theta 1,2 parameter very precisely, as well as seeing through the beating effect of these two oscillations, the possibility to resolve the mass ordering through these means. And so this is an experiment that's coming together very, very quickly. And so despite COVID-19, they are still claiming that they will complete the experiment next year and start data taking in the year after. And so it will be very interesting to keep an eye on this and see what comes. I'd like to turn over to accelerator-based experiments. And so the nice thing here is that there's a common theme about how we produce neutrino beams with high energy protons, which impinge on a target. We produce pions, and those pions, because they overwhelmingly decay to muons and muon neutrinos, allow us to produce intense beams of muon neutrinos and muon antineutrinos, depending on the sign we focus, of pions that we focus. And so by focusing pi plus, we get mu beams. By focusing the pi minus, we get the mu bar beams. What I show you here is obviously a cartoon, but every step of this represents an enormous technical challenge, especially as we scale the intensity frontier, with now proton beams achieving something like a megawatt of power, approaching a megawatt of power. And then there's the horn focusing, which is and other components which have to survive in a very harsh thermal and radiation environment to deliver this beam. So typically the accelerator-based neutrino beams will produce neutrino energies of around a few GeV. And so what you see here, for example, is a spectrum from NOVA in purple, one of the experiments, and another one, the T-decay in orange, which are sort of the currently running experiments. There's a technique to actually point the beam slightly away from the detector, which allows you to lower the energy to the beam and make it narrower. And basically that technique can be used to maximize the oscillations based on the distance to your detector. And so to set this ratio in such a way that the oscillations are maximum where you place your detector. And so at this energy, we can basically make two measurements, or four if you include the antineutrino channels. One, which is the muon neutrino disappearance, which is primarily sensitive to sine squared 2 theta 1, 2, 3, 2 theta 2, 3, and then the mass differences. And then the nu mu to nu e oscillation channel, where we can probe sine squared theta 2, 3, the CP pi violating parameter delta, as well as to observe the matter effect, which is sensitive to the mass ordering. And so on the one hand, the good news is that that we're sensitive to all these parameters. The bad news is that we have to somehow disentangle the effects of all these parameters to inform what we can say about any given parameter, for example, the CP violating phase. So the two experiments, as I mentioned, are T-decay, one of which is in Japan, which sends a neutrino beam of around 0.6 GeV, or 300 kilometers across Japan, from Tokai to the Super Kamiokande detector. The other one is NOVA, which is produces a beam at Fermilab, which is sent to the NOVA detector about 800 kilometers away. And so you can sort of see that there is a factor of 3 difference in energy, and therefore the distance is about a factor of 3. And so both experiments, through very different means, have very powerful means of separating the neutrino flavor. You have these sharp Cherenkov rings for muon neutrinos in Super K, whereas you have a very clean muon signature, tracking signature in NOVA. Likewise, the showering profile of an electron in Super K is very clean. And as you can see, through a tracking detector like NOVA, you also get a very powerful capability to identify these events. And so just to give you some idea about the complementarity of these experiments, the two plots above here show the oscillation probabilities at T-decay. in normal hierarchy. And so here you can sort of see the difference between delta Cp equals 0 versus minus pi over 2. And so there is an enhancement for neutrinos and a suppression for antineutrinos. And you can also see, even in the case of delta Cp equals 0, there is a small difference that arises from the matter effects. And so overall at T decay, the matter effects are I wouldn't say very small, but they are secondary. Whereas if you go to nova, what you see is that the mass ordering has a much bigger impact. And so the nova has a much greater sensitivity to the matter effects, but then also have to compete with the effects from delta Cp. Okay, so what do we see at these detectors? First, if we look at the muon neutrinos, what we see in both experiments is that a very large disappearance effect. And so this is the energy spectrum of neutrinos we see in neutrino mode and muon antineutrino mode for nova, and also in T decay. And so if we plot the ratio of the observed events versus what we expect for no oscillations, you see that this almost reaches 0 in both cases, and which is indicating that the muon neutrinos at the oscillation maximum have nearly completely transformed into other neutrino flavors. And so both experiments are consistent with what we call the maximal oscillation with theta 2,3 around pi over 4. Now, if we go over to the electron neutrinos, here on T decay, you see the electron neutrinos that we see in the neutrino beam, and also with the antineutrino beam. For nova, that they have different bins of depending on how certain they are about the event classification. So here we have electron neutrinos, and here we have the antineutrinos. So both experiments actually see very clearly nu mu to nu e oscillations. As you can see from the right plot, nova also has very clear channel indications of the appearance in the antineutrino channel, whereas with T decay, it is still not quite statistically significant. But this does have implications for the results seen from the experiment. In some sense, the T decay experiment is indicating that the nu mu to nu e channel is favored over the nu mu bar to nu e bar channel, or this is enhanced, this is suppressed. Whereas nova sees a sort of a more balanced picture between these two things. And so that leads to quite different conclusions from the two experiments. One which is saying sort of a maximal Cp violation, normal ordering. And for nova, this is a more ambiguous statement. And so this can be seen if we look at the results more formally. I'm afraid I have lost the horizontal axis here. But what we see here is the allowed regions in normal hierarchy for nova, sine square theta 2,3 versus delta Cp. And this is the 3 pi over 2, where the oscillations in neutrino mode are most heavily favored over the antineutrino mode. And so the T decay results favor this region, whereas nova, because the observed probabilities are more even, basically doesn't have much of a preference, except for maybe where the T decay result is favored. If we look at the other parameters, the sine square theta 2,3, which is also primarily driven by, also has a high impact for the nu mu disappearance measurement, you can see that both experiments are quite consistent and making precise measurements, and both experiments remain consistent with the maximal mixing, though nova may have a very, very slight preference to move away from them. Okay, so that is the current situation in long baseline experiments. There are a number of exciting experiments which are upcoming. First is the Dune LBNF experiment in the US, where a new neutrino beam, LBNF, will be fed by a new accelerator, PIP2, to which India is making major contributions, to provide a 1.2 megawatt beam across 1,300 kilometers to a detector in South Dakota. And so this experiment will use liquid argon time projection chambers, which have a very powerful imaging capability, and so we hope that this will give us a powerful view on the neutrino interactions which are happening. Another nice feature of this experiment is that it has a relatively broadband beam, and so in addition to the first oscillation maxima, there's a possibility to see the neutrinos which are oscillating for the second time, where things like the Cp violation effects are qualitatively larger, and also provide a very, very interesting look at the neutrino oscillations. There's the upgrade of super Kamiokande to hyper Kamiokande. And so this is basically almost an order of magnitude larger detector relative to super K. And so using the JPark beam, which would be upgraded to 1.3 megawatts, this will allow the TDK program to be in some sense, revitalized at a much higher statistics. Now, another feature of this experiment, which is very interesting, is that the neutrino beam actually appears again in Korea. And so there's the opportunity to place a detector there and also probe the second oscillation maxima by a different means. So in the first, in DUNE, basically, we will go to lower energies to see neutrinos which have oscillated twice. Here we allow the neutrinos to basically propagate 3 times further and to see them oscillate a second time. So I think at least both of these things are very exciting propositions. There's also important development contributions from D-SPICE and C arrays like HAM3net and IceCube, which are already providing very interesting measurements of sine square theta 2-3 and the atmospheric mass splitting. And so in the future, they will continue to improve their precision. But also because of the enormous size of these experiments and their statistics, they are also making very important contributions to the new tab channel and possibly in some ways unique that other experiments certainly have a challenge in probing. So I'd like to mention a few other things. There's the INO experiment, a 51 kiloton magnetized iron calorimeter. So this will be a very unique capability, I think, to do sign selection with detectors which are comparable or larger than those that are already planned. And so this brings a very powerful capability that hasn't existed yet for the study of atmospheric neutrinos. There is a detector concept called Thea, which is sort of combining the benefits of water Trankov and simulation detector technology along with new photosensor detection techniques. And then there's the ESS new B beam, a concept to use the 5 megawatt proton source of the European spallation source to produce a low energy neutrino beam to study the second oscillation maximum. Okay, so I'd like to mention a few anomalies which also Professor Babu hinted at. So there are a number of anomalies which are currently attributed to neutrino oscillations. In particular, there are things like deficits of the anti-electron neutrinos which are observed from reactors, and some people have noted that there is historically an overall deficit, and then more recently the Neutrino 4 experiment even claims to see an oscillation effect within this data. And likewise, there are excesses in electron neutrinos appearing from muon neutrino beams, starting from the LSND experiment, I guess that's almost 25 years ago, and then also the mini-moon experiment, where both in neutrino mode and anti-neutrino mode, the experiments observe an excess of electron-like events over the expectation. And so these, since these experiments are occurring typically on a short baseline, so not over the, let's say, the hundreds of kilometers that we saw previously, but sometimes 30 meters or even less than a kilometer for the short baseline experiments here, they imply a mass splitting of around 1 eV squared, which is actually inconsistent with the standard neutrino flavor framework. And for other reasons, this suggests that there may be additional neutrino species which are mixing with the active flavors. But I have to say that this is a complicated picture. The anomalies are not consistent. We cannot also rule out the possibility that given all these anomalies that, well, we can't say that can be all explained at once, nor can we even, I would say, necessarily say that they are all driven by neutrino oscillations. So it is a very complicated picture. And nonetheless, I think the resolution of these anomalies is very important. And so there is a big program aimed towards this. First is the short baseline program, which basically continues to use the neutrino beam used for mini-boon, but now with 3 liquid argon detectors, one at short baseline, SBND. There's a microboon experiment, which has been operating for some time, and the Icarus experiment, which in fact has just started operating. And so these detectors are at 110, about half kilometer, and 600 meters from the target. And so relative to mini-boon, they have using the liquid argon TPC detector, there's an very important ability to discriminate between electrons and photons, which the mini-boon experiment could not do. And so this will be a very important sort of key piece of information about the nature of the excess observed at mini-boon. And so the microboon experiment, I know, has been working on their analysis for some time. And so I'm very eagerly expecting their results. And as I mentioned before, the Icarus detector, which has made a sort of a global trip from Italy to CERN, where it was refurbished and then moved over to Fermilab, has now been installed and commissioned. or nearly commissioned, but already the detector, parts of the detector are operational and working very well. There's another experiment in Japan called JSNS2, which is using a stop pion beam, which is basically the same signature that the LSND experiment used. And so this is also a very exciting development. The experiment has just started operations, and so I look forward to that as well. And I'm afraid I didn't have a chance to really expand on the reactor experiments, which are in progress, to also continue to probe anomalous disappearance of electron antineutrinos from reactors. So yeah, coming back to maybe Professor Babu's talk, I think there are a lot of interesting mysteries about neutrinos that we continue to ponder about. Why the mixing, whether in quarks or leptons, are the way it is there any connection between them? Why are they so different? And when, in the end, what drives these parameters? There's a question of why the neutrino is so light relative to the other particle. And so I think, yeah, somehow we feel that the neutrino really is, even though it kind of fits nicely into the standard model, is pointing to some kind of different origin story that we are still trying to understand. So let me come to my conclusions. So it's been a golden age for neutrino experiments, and I have to say, people have as long as I've been a particle physicist, have said that it's a golden age, but it seems that continues. And I think what's happening is that every time we learn something about neutrinos, to answer an old question, we get new questions following from those answers. And I think the current experiments already are raising new questions. We know that neutrino masses are tiny. We are still waiting to see whether they show any indication of being a Majorana particle. At least according to one experiment, the neutrino mixing parameters for CP violet shape may be near a theoretically maximal value. I think the experiments agree that theta 2,3, one of the mixing parameters, is mixing angles is close to its theoretically maximal value, and to me, that's something that is begging for an explanation. And then there may be anomalies, really qualitatively new things that may be pointing to exciting new physics. And yeah, I think at this stage we are, sort of, in some sense, the neutrino is telling us a bunch of answers, and we're trying to figure out what question that was an answer to. And so the way I see it is certainly for now and for the next decade and possibly 2 decades or more, the golden age of neutrino experiments will continue. And so I think it will be a very exciting time. So thank you very much.
Thanks a lot, Tanaka-san, for that really comprehensive review on experimental status of neutrino experiments. We can have some questions. Please raise your hand or write in the chat box.
Amol, may I ask a question?
Okay, go ahead.
So Tanaka-san, thanks a lot for this nice comprehensive talk. I have a question. You made a comment about the Juno at the beginning of your talk, and they are doing fine and they are going to take data possibly in 2022. But I would like to hear from you, what is your comment about the energy resolution that they need to accomplish their goal, which is the most important criteria in their experiment?
Yes, I agree that this is a critical aspect of the experiment to be able to how should I say, to basically enable it to reach its goals. It is certainly an extremely challenging one to, there are basically 3 elements to this, right? There's maximizing the intrinsic yield of scintillation photons. There is the attenuation length, so that the photons can actually reach the photon detectors. And then there is the photon detection itself and maximizing the cover surface area and the photo detection efficiency. I have to say that maybe in the past I've been very skeptical about this, as well as even the construction schedule. But you can sort of see that the detector is coming together. They've had some very nice results in showing various scintillation mixes. So I know this is going to remain a challenge, not to mention the systematic uncertainties, but I don't see a showstopper, so to speak. As far as I know, they are on track to reach these goals. They still have a ways to go, but I'm not pessimistic or so skeptical as I was in the past.
Yeah.
Hi. So this year, Borexino was awarded the fundamental prize for their announcement of observing CNO neutrinos. Would you like to comment on that?
Yes, I think this is I'm sorry. This is one of those aspects of the neutrinos that I did not address because I think the solar neutrino program has really started to change in its nature. That now that we sort of have the understanding of the solar neutrinos, the solar, there's no solar neutrino problem anymore. It's a solar neutrino solution, and we're trying to understand various aspects of the solar neutrinos. So I think that's an extremely interesting program. First in probing the stellar dynamics of the sun itself. But yeah, I should perhaps have mentioned that there's also the interesting question of the upturn in the spectrum, or the expected upturn that we still don't see, which is necessary to really verify our understanding of the matter effects which drive the flavor change in neutrino oscillations. So yeah, I can't say anything very specific about it, but to say, yeah, that's a very interesting and exciting program that I certainly did omit to mention.
Yeah, and also, just the understanding of how the stars shine is an extremely important question.
Absolutely, and while I'm at this slide, right, I think there's the possibility of the multi-messenger astronomy that IceCube has recently demonstrated that's also extremely important. There's the neutrino probes the cosmological probes on neutrino mass, both with CMB and large-scale structure, which is also of fundamental importance in understanding the structure of the universe. All these things have extremely exciting prospects.
Indu?
Yeah, hello. My question was also about reactor neutrinos. Sometime back, there was this discrepancy in the flux at around 5 to 6 MeV. Is it still there? Has it gone away? I think many experiments were having this feature.
I think maybe there are two things, right? There is the sort of an overall deficit in the neutrino flux that people have been studying for I can't remember even how long now, just based on some historical data, and that has caused a revisiting of all the reactor neutrino fluxes, which has been quite a program. And I think we learned from that is an extremely complex process. I think when I started neutrino oscillation experiments, people told me that accelerator-based neutrino beams are extremely complicated and you'll never understand them, whereas reactor fluxes are perfectly known and it's the perfect way to do neutrino oscillations. I think the truth is certainly halfway between for each of those cases, and in some sense, while the process of making the pions is complicated, pion decay itself is relatively easy to understand. So there's that thing, and then I think you might actually be referring to sort of the bump at 5 to 6 MeV, and so I think it's clear experimentally that bump is there. It's not an anomaly that is present in one experiment but not the other, and there have been some hints that related to which isotopes within the process fission processes are responsible for that. But my sense is that there's still not really a clear picture of the nuclear physics behind that, and so that will continue to be studied.
Thank you.
We'll take a last question from Professor Datta.
My question relates to this possibility that Catherine only puts an upper bound on the mass of the electron neutrino. If that happens, what is the kind of advance that is needed in prospect? The resolution probably certainly will be better than that in Catherine, but what is the kind of source strength that is required to improve on this measurement and improve by maybe another factor of 3 or 4 sensitivity?
Yeah, so yeah, maybe there are two parts to that. I think, personally, I feel there's a sense that certainly the Mackey filter technique is sort of reaching a practical limit. And so that's why experiments like Project 8 and others are looking at new techniques for the spectrometry side. But your question is actually related to the source and how much more intense the source, how much more tritium do you need to make a qualitatively new step beyond the expected sensitivity of Catherine. I'm afraid I can't answer that question. I know certainly the source for Catherine itself was a big challenge, and what challenges there are to get something 10 times more intense or 100 times more intense. I don't know. I'm afraid.
Thank you.
I'm sorry.
So let's thank Tanaka-san.
Okay, well, thank you very much again.
Thanks a lot. The next speaker is Sandhya Choubey. Sandhya, can you share your slides? Tanaka-san, can you unshare your slides, please? Thanks.
Is that okay?
Yeah, that's fine. Please start.
Okay, so good evening, everyone. We had two very good talks on neutrinos, and mine will be roughly talking the same things that we've been hearing for the last an hour and a half. So I'll be talking on future prospects in neutrino physics. And so let's start by just listing down what we have next on the agenda. So we want to confirm we already have an almost 3 sigma hint from the currently running neutrino experiments T2K and NOVA that a CP phase for the leptons, for the neutrinos, could be minus pi/2, but we still want high significance confirmation coming from future experiments. We also want a very precise measurement of the CP phase, because it's important for from the theoretical point of view to know exactly what is the value of the CP phase, just in the same way that we wanted to know what exactly is the value of the mixing angles and the mass square differences. Then we already heard a bit about the issue on the neutrino mass orderings in the previous two talks, and I will focus more on what are the prospects coming up in the future. We want to know the octant of θ23. So what exactly is this octant of θ23? So θ23 so far has been essentially measured in experiments that have been sensitive to the muon neutrino survival probability, where the leading term, the leading oscillatory term, depends on sine square of 2 θ23, which means that for any measured value of this survival probability, you always have two values of θ23 on both sides of pi/4. So there is a θ23 and then there is a pi-2 of θ23, which give you exactly the same or almost the same value of p mu mu. And so the current experiments are kind of not very good at distinguishing which of the two values of θ23 lying in the two octants, the lower octant and the upper octant of θ23 entire parameter range, is the correct value of θ23. So we want to know the octant of θ23. And of course, from theoretical point of view, we want all parameters of the neutrino sector to be measured to almost the same precision that we have in the quark sector. Then once this program is done, of course, we can now go ahead and look for subdominant effects. We know that neutrino masses and mixing are the leading reasons for neutrino flavor oscillations. But at the subdominant level, we could have signatures of new physics in neutrino oscillation experiments. And we are, of course, now as a next on our agenda, we want to probe these subdominant effects and constrain models of beyond standard model. Then, of course, we have had some discussion on whether the neutrinos are Dirac or Majorana. In this session, also in one of the earlier sessions today, where we heard about possibility of using xenon to look for Neutrinoless double beta decay. We are still hopeful that at some point we will have a supernova exploding in our own galaxy, releasing a huge flux of neutrino-antineutrino pairs. And our current detectors that are running across the world are very much equipped and would give a signature in the neutrino channel, which would have far-reaching implications both for neutrino physics as well as astrophysics. Now, in this context, there is a possibility of measuring the diffuse supernova neutrino background. So what's diffuse supernova neutrino background, or DSNB as it's normally called? It's essentially the neutrinos that have been released by all past supernova from the time that the stars first exploded until today, and they kind of permeate the entire universe. They are redshifted in energy, and so far we've tried, but we've not been able to have any positive signal for the diffuse supernova neutrino background. However, this year, Super Candy has been loaded for the first time with gadolinium, and this has been done in order to reduce the background in Super K, which is going to help Super K to be able to unambiguously give us a signature of the supernova, the diffuse supernova neutrino background. So I'll not be discussing any details about this possibility, but this remains as one of the most relevant things that we can look up to in the very near future. Then, of course, we've had some mention of observing ultra-high-energy neutrinos at neutrino telescopes. And this is, of course, a thing for the future, the thing for the future, where, of course, we want to combine observations in neutrino channel along with observations in, say, gravitational wave and in the gamma rays and photons in gravitational waves and in neutrino together to understand our universe better. So, of course, in this talk, I won't be covering everything, but roughly the part which is highlighted at this moment is what I'll be focusing on in this talk. So, CP violation, why bother? We already had some discussion on this. It's an important parameter of the neutrino mixing matrix. And it's, in fact, one of the key parameters in models of neutrino mass. And this measurement of the CP phase could be actually an effective pointer at identifying the correct BSM model that would explain neutrino masses in addition to all the other observations that we have, which point towards a theory of beyond standard model. Then, of course, once you have seen CP violation in neutrino oscillation experiments, it doesn't guarantee that leptogenesis must have happened in the early universe, but at least it kind of gives you some kind of a reason to believe that if CP is violated in neutrino oscillations, there could have been a possibility of leptogenesis being the reason for the creation of the matter-antimatter asymmetry in the universe that we have observed. So how do you see CP violation? Essentially, you want to see a difference between the neutrinos and the CP conjugate state, the antineutrinos. So if you make any observations which tell you that the neutrinos are behaving differently from the antineutrinos, then effectively you've observed CP violation. Now, in the context of neutrino oscillation, it essentially comes in the neutrino mixing matrix, the PMNS, the so-called PMNS matrix, where this phase here appears along with the mixing angle θ13 in the PMNS mixing matrix. Of course, in addition to this CP phase, which is called the Dirac CP phase, for obvious reason, because this phase is a phase which the neutrinos would have irrespective of whether they were Dirac or Majorana particles. So in addition to this so-called Dirac CP phase, we have actually possibility of 2 additional phases in the case of neutrinos. But these phases make any kind of phenomenological implications only if you were sensitive to the fact that the neutrinos were Majorana, which essentially effectively tells you that Neutrinoless double beta decay is the only relevant experiment that you can look forward to in order to observe the Majorana phases, which I have named as alpha 1 and alpha 2 in this slide. So the best way to look for CP violation, this effect of this Dirac CP phase delta CP, is to look for the conversion of muon type neutrinos to electron type neutrinos. And so this is the so-called P mu E channel, which depends on a large number of oscillation parameter, but it does depend on the delta CP. So it depends on both sign of delta CP as well as cos of delta CP. And essentially the sign of the very fact that it depends on sign of delta CP makes this channel very attractive, because when you go from the neutrino to the antineutrino channel, delta CP changes sign. It becomes minus delta CP from delta CP, in which case this term here Phillips sign between the neutrino and the antineutrino channel. And now if you make an accurate enough measurement of P mu E in neutrinos and antineutrinos separately, compare the data in the neutrino and the antineutrino channels, you should have a clear indication of whether CP violation has happened in your observation, whether you've seen CP violation in your data or not. So we've heard about how we have used accelerator beams currently, and we plan to use them in the future. In the previous talks, essentially we accelerate protons to very high energies, make them impinge on a fixed target, creating pions, and these pions then decay to create a muon type neutrino beam. So you are looking for muon neutrino oscillating into electron neutrinos, and if such oscillations has happened, then of course you expect to see some electrons in your detector, in your as your signal. Then the muon type neutrinos that remain unoscillated, of course, would then be detected in the detector in their muons, in terms of muons. So now, in order to be able to observe CP violation, which is a very tiny effect, we saw that it was suppressed by the mixing angle θ13, which is a small parameter. We need to have an experimental setup which should essentially satisfy most of these criteria. So we need a very high intense neutrino beam. So we should have a very high flux of neutrinos coming to the detector. And also, we could also have a big detector. So in order to increase the statistics, we need an intense beam and a big detector. We, of course, should be very mindful about the systematic uncertainty. We'll see in a plot how the systematic uncertainties very quickly reduce the precision of your experiment to CP violation. We need good energy resolution. We've seen some of the probability plots in the earlier talks where we saw that the CP sensitivity of the oscillation channel did have an energy dependence. So it's very important to be able to reconstruct the spectrum of the neutrinos that you're observing. There should be a good particle ID. This is essential, very essential in order to reduce the backgrounds. And of course, you need, you should also reduce all kinds of other backgrounds that you might have in your detector. So we already have had some exposure to some of these names, the forthcoming experiments that we are looking forward to give us a very high significance evidence for CP violation in neutrinos are the following. The first that I would want to discuss is the T2HK experiment proposed to be built in Japan. So this experiment is going to send a very high intensity neutrino beam created at the JPAC facility there to the hyperkamikande detector. So that's the layout, that's the cartoon of the hyper-K setup to be built in Kamioka. And this is the status of the project. The hyperkamikande project is now officially approved by the Japanese government, and it is actually under construction. The operations are scheduled to start in 2027, and this is like 7 years from now. KK simultaneously is going to upgrade the JPAC accelerator beam to create the high intensity neutrino beam that we need for the physics goal of T2HK. Now, this megaton class water Cherenkov detectors, this box here lists the detector specifications, some of the most important one, and how it differs from its parent Super K. So this detector, this very large megaton class water Cherenkov detector would actually have a very rich physics goal, and some of them I've mentioned here on this slide. So of course it can be used for, it is being built to actually detect the neutrinos created at the JPAC accelerator facility. But in addition to that, it has a very rich physics program. It's very sensitive to, it would be very sensitive to a galactive supernova burst. It would be able to detect very effectively the diffuse supernova neutrino background. It's going to give us one of the best limits so far on proton decay. It can be used for indirect detection of dark matter, in particular from neutrino fluxes coming from annihilations of WIMP type particles in the center of the sun or at the center of a galaxy. It can still be used to study solar neutrinos and give any missing information that we might have and which we might actually hope to learn by observing solar neutrinos. It's going to observe atmospheric neutrinos, and I'll be discussing about that in a moment. So this is a snapshot of the Super Cavalcanti Proto collaboration, and I am a member of the Swedish group of Hypercavalcanti. India, of course, also has institutions that are participating in the Hypercavalcanti project and hope to contribute to the R&D of this fabulous experiment. The next, of course, is the DUNE experiment to be built in the US, and we've also heard about DUNE. So the idea here is to create a high-intensity neutrino beam at Fermilab and shoot it at a distance of 1,300 kilometers to South Dakota, where they are expected to be observed in this in the home state mine. So there'll be an upgrade of this underground lab facility, where we want to place a 40 kiloton FAR detector to observe the high intensity beam sent from Fermilab. And this is the layout of the cavern. They're going to be near detectors. So there's this near detector feature is a common feature for all the experiments that all the long wavelength experiments that we are talking about today, the Hypercavalcanti DUNE, and I'll be talking about ESS NUSB in a short while. They all have plans for multiple near detectors, and the near detectors are extremely important for reaching the physics goals of these next generation long baseline experiments. This is a figure which shows the flux of the neutrino flux planned to be created at Fermilab, and we see from this figure that these neutrinos will be roughly of 2 GeV energies. Now, this is important. I did not mention this, that in the case of Hypercavalcanti, because the distance there was only 295 kilometers, the hyper K beam is going to be only of about 0.7 GeV in energy. And we'll see in a moment that that actually makes the T2HK experiment in principle slightly different from the DUNE experiment. So to that in a moment, but for now, we are focusing on just CP violation, and both experiments are as far as the beam energy and the baseline is concerned are operating, are in fact due to operate on the first oscillation maximum. So this is a snapshot of how the DUNE collaboration looks. Of these 33 countries, I must mention that India is one of them. There is a very large number of physicists in India who are a member of the DUNE collaboration, and I was also a member of DUNE for as long as I was in HRI in India. So the third experiment, of course, is closer to home for me. It's the ESS NUSB project, proposed to be built in Europe, in particular in Sweden. So the idea here is to have a facility. So there's already an ESS facility in Lund, which is being upgraded for experiments in nuclear physics. And there's a proposal to have a neutrino beam at ESS Lund. And this neutrino beam would then be sent to a FAR detector. The FAR detector, of course, is going to be a megaton class water Cherenkov detector, maybe slightly bigger in size than as compared to the Hypercavalcanti. While there are various baseline options open for this experimental proposal, there are only two that are being seriously considered. So there is a proposal to send the beam at 540 kilometers, which will place the experiment exactly at the second oscillation maximum. There is also now talks of sending the beam to another detector location at 360 kilometers, and 360 kilometer with the current, of course, beam option that we have for ESS NUSB would essentially mean that the experiment will be performing somewhere between the first oscillation maximum and the second oscillation maximum. And the R&D is currently on, and decisions are being made based on the physics goals and the physics outputs of the two detector options, on which one will be finally chosen in the final plan. So this is the beam option because this experiment wants to do this proposal wants to do the experiment at the second oscillation maximum, at least for the 540 kilometer baseline option. The energy of the beam is even lower than we have for T2HK. So this is mostly at around 0.4 GeV neutrinos that we are talking about. Again, this experiment will have multiple near detectors. So there'll be some fine-grained near detectors and some smaller water Cherenkov detectors. And these detectors will be placed along the beam line. So the very fact that this experiment will be done at the second oscillation maximum makes this experiment very different from T2HK and Dune. So this is the timeline for the experiment. So currently there are 15 institutes in 11 European countries that are participating in the design study of VSS USB. So currently we are here. So there's one phase of this timeline that is coming to an end in next year in 2021, which was funded by EU H 2020. And if everything works out, this experiment is expected to start data taking in 2035. So here is what we expect from these experiments for CP violation. And we see that all three experimental proposals have excellent sensitivity to CP violation. The parts that I have shaded essentially tell you that if delta CP, if the true value of delta CP lies within these shaded bands, for the three plots that I have on the screen right now, we would be able to exclude, we will be able to confirm CP violation, which means that we will be able to exclude the CP conserving values, which essentially means delta CP of 0 and delta CP of 180 at much more than 5 sigma. In fact, this lines I have put at 5 sigma. So we will have a 5 sigma discovery of CP violation at these experiments for a very large set of possible values of delta CP. Now, in this slide, I want to just mention some of the challenges that these experiments could face. So here we see how the sensitivity of T2HK goes down as you increase your systematic uncertainty. If you had no systematic uncertainties, then you would be able to have a 5 sigma significance of CP violation at the end of even before 2030. But if you if we use the T2K systematic uncertainties, we would have to run this experiment at least until 2032. This here slide here shows how the statistics affect our significance of observing CP violation. So of course, I mean, there are challenges which these experiments need to overcome. Then, of course, measurement of the CP phase is one of the key goals of these experiments. So once you have established CP violation, you also want exactly the value of the CP violating phase. And these plots tell you how well we will be able to actually measure the value of delta CP. And just a very quick look at these plots tell you that we will be able to know delta CP down to an error of roughly 10 degrees. Again, here, I mean, you can actually make various comparisons. This plot here tells you that the 540 kilometer option, which is this green line, is actually worse compared to the 360 option, which is this line, if delta CP indeed turns out to be minus pi by 2. So these are the considerations that are still being deliberated upon for these forthcoming experiments. So next, very quickly, neutrino mass ordering. We already have seen what exactly is the problem in Babu's talk. Essentially, we don't know the sign of delta m square 3.1, which tells us that either of the two mass spectrum are possible, and we want to know which one is true, which means that we want to measure the sign of delta m square 3.1. So essentially, the neutrino oscillation probabilities always depend on the sign of delta m square 3.1 because we have this term here in the neutrino oscillation probabilities in vacuum itself. However, there are degeneracies between this term, this oscillatory term here, and these mixing matrix elements term there. And so this is actually in practice, it is not possible to measure the sign of delta m square 3.1 using this oscillations in vacuum, which means that we need matter effects to distinguish oscillations with delta m square positive compared to oscillations with delta m square negative. And in a nutshell, this is what happens when neutrinos travel in matter. Then the nu type neutrinos, of course, will have scatterings of electrons, because we only have electrons in normal matter. Neutrinos and antineutrinos of electron types forward scatter of electrons, and in the process they pick up a potential. This potential has a difference in sign between the neutrinos and the antineutrinos, just from the fact that the antineutrinos are the antiparticles. Now, just the presence of this extra potential in the propagation equation modifies the mass and the mixing angle of the neutrino, and this is how this modification happens. So this is in the two generation limit. However, the same thing holds even when we consider all three generations of neutrinos. And notice that for any matter effects to be significant, we need a relative. So the relative sign between delta m square and A is very crucial, which means that if delta m square was positive, we would want A to be positive, which means that for normal ordering, delta m square positive, it's actually the neutrinos that will have matter effects. Whereas for inverted ordering, which means delta m square negative, we want the antineutrinos, which come with a negative sign for A, will actually experience matter effect. We hope to use these properties in oscillation experiments to give us sensitivity to mass hierarchy. Now I said Dune will operate at 2 GeV, while T2HK and ESS NUSB are going to operate at less than 1 GeV. All three experiments have very similar baselines, which means that they see the same matter effect. If you go back and look at this thing A, which is essentially the matter potential, this matter potential depends on the matter density, which is Ne, and it also depends on the energy of the neutrino E. So since the matter density is essentially the same for ESS, Dune, and T2HK, it's essentially the energy of the neutrino, which tells you which experiment is sensitive to matter effect and which is not. And in the case of this forthcoming long baseline experiment, turns out Dune is very sensitive to matter effect. It's expected to see large matter effect. In fact, matter effect in Dune is going to be good enough to have a very high sensitivity to the neutrino mass ordering. And we can, irrespective of what is the value of delta Cp, we do expect some, we expect sensitivity to almost 7, 8, 10 sigmas in statistical significance. Then, of course, neutrino, we have atmospheric neutrinos. Now, these neutrinos travel through the Earth matter diameter. So they actually not only have possibilities of all energies. So we have atmospheric neutrinos going from very low energies to tens of TeV. We also have possibilities for the highest possible matter density inside Earth. So these neutrinos, of course, are designed to observe matter effects. And again, it's the same detector setups that are now going to play a role. So we have the Hyper K in Japan. So the crucial points of Hyper K, that it's going to have good zenith angle resolution. It can distinguish the electrons from the muons. It has a low energy threshold and very large statistics. It's a huge experiment. The Pingu and the Orca, they are very similar to the water Cherenkov detector, except for the fact that these are even bigger than ESS, NUSB, and Hyper K. Then, of course, we have INO, and so this is, of course, very close to the heart of many people here present today in this talk. So INO, of course, is different. It's a magnetized iron detector, and the selling point of INO is that it's going to be magnetized, which means that it's the only detector which has the potential of distinguishing the neutrino from antineutrino. And I just spent a minute on stressing the point that the neutrinos and the antineutrinos, they, of course, have opposite roles to play as far as matter effects are concerned. And because atmospheric neutrinos come with both neutrino and antineutrino at the same time, this automatically gives INO an edge over all the megaton water Cherenkov detectors as well as the neutrino telescopes. So this slide here tells us the prospects as far as mass hierarchy is concerned, we see that all these experiments could give us a more than 3 sigma sensitivity in some due course of running. So they're not going to be as sensitive as Dune, but of course this will be an independent confirmation coming from a completely different kind of neutrino source. Now, one thing which is not apparent in this slide is that I mentioned that INO has an edge in terms of charge ID. So all these plots have been generated using normal hierarchy as true. If you generated the same plots with inverted hierarchy as true, you would see that the sensitivity of hyper-K and ESS NUSB, as well as the sensitivity of Pingu and Orca, would go down considerably. But the sensitivity of INO actually remains the same. And this is because of charge ID. Then, of course, I should mention Juno before I move on. So Juno is an experiment which is going to start operations before any of the experiments we are talking about right now. And Juno would give us a 3 sigma mass ordering sensitivity in 6 years. One thing I would like to point out in the context of Juno, which is written here in this table, is the remarkable precision that is going to return in terms of the mixing angle theta 1, 2, the value of delta m square 2, 1, and the value of delta m square EE, which essentially tells us the value of delta m square 3, 1. So this is unprecedented precision ever in terms of neutrino oscillation parameters. Octant of theta 2, 3 also can be measured at both in the atmospheric neutrino experiments weak, but it can be done pretty well in the long baseline experiments. So I should very quickly now go and spend the last few minutes of my talk on the prospects of observing subdominant effects coming from new physics in neutrino oscillation experiments. So of course, you will be able to be sensitive to new physics in the neutrino oscillation experiments if and only if the neutrino oscillation probabilities themselves get modified because of the presence of the new physics. So here I've listed some of the new physics scenarios which can actually change the neutrino oscillation probabilities and hence the data in the neutrino experiments. So we already have heard a bit about the sterile neutrinos. We also have heard about non-standard neutrino interactions. I'll be talking very briefly of the possibility of neutrino decay. In addition, you can have non-unitarity of the PMNS matrix coming from some kind of a new physics scenario. It could be sterile neutrino or some higher scale physics, which is bringing non-unitarity in your PMNS matrix. You could be looking at Lorentz invariance violation, which is going to affect the propagation of the neutrinos. You could have CPT violation. You could have large extra dimensions. You could have long-range forces affecting neutrino propagation. There are myriads of new physics scenarios which actually indeed change. Decoherence is a very hot topic when we discuss neutrino oscillations in context of new physics. So there is a possibility that these new, bigger and better experiments could open up a channel of looking for new physics in neutrino experiments, which could be complementary to looking for new physics in other kinds of high energy experiments that we are interested in. So we already have seen this plot. LS10D had seen a 3.8 sigma excess in their anti-neutrino challenge. LS10D was an accelerated experiment producing a mu beam and looking for electron appearance in the final state in their detector. And then this was independently checked by Mini-Boon. And after a lot of data releases and many years of running, Mini-Boon has finally confirmed that they are consistent with the LSND excess in electrons, both in the neutrino as well as in the anti-neutrino channel. And combined with LSND, they claim that they have a greater than 6 sigma excess of electrons in their experimental data. Now, if we fit this using the sterile neutrino hypothesis, and if we add one additional sterile neutrino, which is popularly known as the 3+1 scheme, then this is the kind of plot that you would expect in the delta m square versus sine square 2 theta plane. And the best fit comes here, which tells you, which gives you a mass square difference of roughly 0.1 and a mixing angle rather large. Now, such a heavy neutrino is and in fact, a sterile neutrino. It has to be a sterile neutrino because it is the third delta m square that we have to accommodate. We cannot do it with 3 neutrinos, so we need a fourth one. So these sterile neutrinos are severely constrained from cosmology, both in terms of the total, the sum of neutrino masses, and also the number of effective degrees of freedom. So neither the cosmological data is consistent with significantly more than 3 neutrino species in the early universe, nor is it consistent with sum of neutrino masses which are more than a few of 10 to the minus 1 eV. Not only is it in tension with the cosmological data, it's also in tension with a large number of experiments that are sensitive to neutrino oscillations. And this is a list, it's a huge list. There are so many experiments which are in direct conflict with the LSND and the mini-boon with the data. And of course, this is going to be tested in the short baseline neutrino program at FNL-AL and the JS-NS2 setup in Japan, as we heard in the previous talk. Before I move on, I must just mention that there is a similar anomaly in the Nu-E channel, where of course there are two kinds of signals that we have seen. There is a problem in the Nu-E bar channel where the reactive fluxes are measured to be significantly less than predicted by the theory. And in the Nu-E channel, where calibrations of the solar neutrino experiments, the gallium experiments, showed that we were actually seeing less number of neutrinos than expected. And of course, there are a large set of experiments that are currently taking data in order to probe this anomaly. And of course, there'll be some more that will be taking data in the future. Here, the thing is in fact more murky because some of the experiments are actually kind of consistent with the sterile neutrino. Now, what I'm going to...
Excuse me, you're about 5 minutes.
Okay, thank you. So what I'm going to in fact focus on next is how we are going to, how we could use the long baseline setup that we were discussing in the past to look for these new physics signal. In particular, right now we are talking about sterile neutrinos. So all these experiments, like I said, are going to have multiple near detectors. So along the beamline of these experiments, we will expect to have very high quality near detectors placed at different baselines. So in this work here, this work here actually looks at the possibility of constraining the sterile neutrino setup, in fact, checking LSND using the Dune near detector. Very similar work can be and has been done for ESS NUSB and also for the T2HK setup. So this is the LSND allowed area. And these are the exclusion plots that we expect from the near detector in Dune. So the near detector of these long baseline experiments are pretty good in excluding or confirming LSND. The far detector of the long baseline experiments will also have a role to play because it's now well known that the neutrino oscillation probabilities at the far detector does depend on the presence of the sterile neutrino. Of course, the oscillations due to delta m square 4.1 itself averages out because the oscillations are too fast. However, it still leaves an impact on the oscillation probabilities. This probability plot here shows you the difference between the probability that you expect in the case of 3 neutrinos compared to what you expect in the case of 4 neutrino. And very clearly, you see that the probability is different between the two cases, which means that the long baseline experiments will have something to say for the sterile neutrino mixing parameters. Now, there are a lot of papers that have been written on this topic, and I had only 3 options. Either I referred to all of them, or I referred to my own papers, or I did not refer to anyone. So I thought that the third option was the best option to choose at this point. So I'll show some plots, but I'll not refer to anybody. So I'm sorry if you were expecting to see your name and it doesn't appear here. So one way the long baseline experiments can be used for studying sterile neutrinos is that the data from long baseline experiments can be independently used to constrain the sterile neutrino mixing parameters. So I said that it can be done at near detectors, but it can also be done at far detectors. The far detectors turn out to be slightly less sensitive as compared to the near detectors. But nonetheless, it's an independent measurement. Then on the other hand, the presence of the sterile neutrino mixing parameters does modify the standard oscillation physics that we want to measure at the long baseline experiment, and for which the long baseline experiments are being built using billions of dollars. So this plot here is a sample plot. It just shows you that what you expected in the 3 neutrino case is the broken line, but if you had sterile neutrinos, depending on which scenario you were actually looking at, you could have a modified expected sensitivity. Now, there is a third and a very interesting possibility, which is that when you go to the 3 plus the 4 cross 4 neutrino mixing matrix, then of course, in addition to the sterile neutrino mixing angles, you also pick up 3-dimensional sterile neutrino phases, 2 in fact, which are physical. And it's not possible to study these phases at the short baseline setup, because at the short baselines that are actually being built to actually probe the LSND signal, it's essentially a 1 mass scale dominance scenario, which means that if you are sensitive to only one frequency of oscillation, you cannot actually be sensitive to CP violation. However, if you go to the longer baselines, you are actually sensitive to oscillations coming from, in fact, all the 3 frequencies. And here, of course, you have the possibility of studying the new sterile phases. And so you have sensitivity to additional CP violations. So this plot here shows a sample study in that direction. Now, in maybe 1 or 2 minutes, neutrino decay. So we don't have any indication on why neutrinos should be unstable, but in case they are. So in case you have this possibility that a neutrino, nu-I, it could be nu1, nu2, nu3, could decay into another fermion, which is I've written as nu prime, and some kind of a scalar or a pseudoscalar. So in the case of, say, the Myron model, which was discussed in these papers here, this J was actually the Goldstone, the Myron. And this would be then a lifetime for the neutrino in this kind of a theoretical setup. Now, if neutrinos were to be unstable, it's but obvious that if the neutrinos are traveling, they will just go on decaying into something else. And if you just assume that this something else, this nu prime, is a fermion that that doesn't have any coupling to the standard model. For instance, if it's a so-called sterile neutrino, then of course you will not be able to see this fermion in your detector, and this is what is generally called invisible neutrino decay. Now, in that case, you can write down the oscillation probability in the 2-generation setup, and this is how the lifetime of the neutrino enters the probability. So it enters the probability in 2 places. It overall suppresses the neutrino flux. It also changes the shape of the neutrino oscillation probability. So you have 2 ways of looking for neutrino decay in your data. You can actually look for lesser number of neutrinos than you expected in the case of standard oscillations, or you could look at relative difference in the spectral shape of your data. So such studies have been performed by not as many as we have for sterile neutrinos, but there are a large number of studies done in the literature. And this table here kind of compiles all the expected. So the top parts are the limits that we have on the lifetime of the third neutrino mass eigenstate coming from current data. So T2K nova combined or T2K plus minus. This is what we expect, what we have from the superchemicande and the Minos data. And this is what we would expect from the forthcoming experiments. So now very quickly to conclude, we are expecting to confirm CP violation in the next generation oscillations at much more than hopefully 5 sigma. And this is going to have far-reaching implications for both the theoretical models of neutrino masses and mixing, as well as for leptogenesis. Neutrino mass ordering, of course, also needs to be discovered at a high significance. And this we can do from the Dune experiment or from the atmospheric neutrino experiments. Theta of octant of theta 2,3 is also very important from theoretical point of view, because most model could distinguish between theta 2,3 being in the lower octant or in the higher octant. And this too, even though it's slightly more difficult to ascertain the octant of theta 2,3, it will be measured to somewhat high significance unless theta 2,3 turns out to be very close to maximal. We do expect to see new physics in the next generation oscillation experiments, or if we don't see, we hope to at least put some limits on the new physics parameters using data from the next generation neutrino experiments. We do look forward to the future, and we do feel that in the next decade, we will be in a much stronger footing as far as high energy physics is concerned than we are today. So thank you, everyone.
Thank you, Sandhya, for this nice review. Any questions for Sandhya? Please raise your hands or write in the chat box. So while people are writing, let me squeeze in the question of my own. You perhaps did not mention it, but Tanaka-san mentioned about JSNS2, which is will try to reproduce LSND results. And my question was going to be, of course, it's more of an experimental question about what is it that JSNS2 will do, which is different from what LSND did. Of course, they have the same decay channel, but do you know anything about what exactly is they do differently?
No, I am not aware of, anything really smart that these next generation experiments are hoping to do in comparison to. Well, one thing I can mention is that both SBN and JSNS2 are going to employ multiple detectors. Now, this is in the same spirit as the long baseline experiments, where the near detectors are being put, and of course also the reactor experiments, where the near detectors have a very important role in removing all uncertainties coming from the beam itself.
Mm-hmm. Okay, Shivavati?
Amol, I can just add to this question.
Just wait, we'll take the other questions first.
Sandhya, very nice talk. I wanted to ask you one thing that, there are also studies on combining various experiments to utilize the complementary features. So would you like to make any comment on that?
Yeah, thank you for bringing that up. I mean, because of lack of time, I did not actually go in that territory. Of course, like I tried to stress in whatever little time I had. I know I was going very fast, but I tried to stress that even though these different experimental setups appear to be very similar, there are subtle differences between them, and which means that the data that they're going to collect will also have that subtle differences in terms of basic physics. And that essentially then means that if you combine data from different experiments, you are bound to overcome those so-called challenges that I was talking about, especially when it comes to the underlying physics itself. So like if we combine data from an experiment that is operating on the first oscillation maximum with data from an experiment that is operating on the second oscillation maximum, we do expect to gain something. In the same spirit, when we combine data with experiment which is running at low energy with an experiment that is running at a high energy, there could be differences, say, in terms of matter effect, also in terms of the distance over which the neutrino is traveling. So like in the case of neutrino decay, it does matter what is the energy of the neutrino and what is the baseline. And the L by E dependence of neutrino decay is very different from the L by E dependence of neutrino oscillations. So when we place all experiments at the first oscillation maximum, it's actually the first oscillation maximum of standard oscillations. But this is not the same L by E for other kinds of new physics. So it does matter a lot when we combine experiments. Then of course we could combine two completely different classes of experiment. Like we could combine atmospheric neutrino experiments with long baseline experiments. And many of us here have been involved in that kind of research for long. And we have seen that there are distinct synergies. One kind of synergy I wanted to point out, and I did not, is the synergy between experiments like Pingu with experiments like Juno, which don't have any matter effect at all. So there was a recent paper by the IceCube collaboration where they studied how much their mass hierarchy sensitivity would improve if they combined Juno with IceCube, with Pingu.
Okay, thank you.
Indu?
My question was related to the LSND mini boon result. There was, I mean, it took so long to settle this question because of uncertainties in the cross sections. Now that will never go away, right? Is there still a satisfactory resolution of those issues, especially because all these experiments are at slightly different energies and they're looking at different channels of, whether it's quasi-elastic 1 pi, resonances, and it's very murky out there, right? Different detector target materials.
Yeah, so I mean, of course, you probably know much more about cross sections than I do, but from what I understand is that particularly at Fermilab, because they have a large number of different kinds of detectors there in Fermilab, and this is something that they have also pointed out in their presentations. Because they have many different kind of detectors, they have neutrinos interacting in various types of targets. So like you in fact pointed that out just now, that there are so many different types of material. But on the other hand, I mean, the same thing which you make it look as a challenge can be actually used by experimenters to understand neutrino cross sections in a material independent way. So like SBN is going to have 3 detectors, all very different from each other and at different baselines. So definitely, I mean, they are much better placed than Mini-Boon, which did not have even a near detector.
Thanks.
Professor Datta?
Yeah. My question is, among the detectors that that are being planned for this European spallation source experiment, which you are saying will happen at roughly the second peak, the second maximum, is there also a plan to have something at the first maximum? Because that would be about 3 times less distant, and therefore a detector equivalent would be something like 10 times at least smaller.
Yeah, so I mean, this is what I said was still being studied and debated. So the choice of this 500 kilometers or 360 kilometers that I mentioned for the ESS USB setup is because, I mean, of course, the accelerator location is already known. It's at Lund. And so they have actually gone across Sweden and also in Finland and tried to find mines where it is an existing mines, because they don't want to build a tunnel or a mine in Sweden. That will incur extra costs. So they want to use an existing mine. So there is a mine at 540 kilometers, and there is also a mine at 360 kilometers. Both of these mines would essentially cost same to upgrade to a neutrino, underground neutrino lab. So initially, of course, ESS USB was completely inclined to do the experiment at the second oscillation maximum, and the idea was to reduce. I mean, so there's always this give and take between impact of systematic uncertainties on the CP violation sensitivity and statistics. So if you go to 540 kilometers, you lose statistics, but you gain because you are becoming less and less susceptible to systematic uncertainty. Now, if you do your experiment at 360 kilometers, it's actually somewhere between the first and the second oscillation maximum. even then, I mean, even though you're like in a no man's land, even though you are like neither at the first nor at the second oscillation maximum, so you don't know whether you are actually gaining in terms of statistics or you are gaining in terms of systematics. It so just turns out that if you just run the same code at 360, sometimes 360 is even better than 540. Like I said, that for delta CP precision, actually 360 turns out to be better, and it's solely coming from the fact that when you are at 360, you have much higher statistics as compared to 540. Now, this question of tuning, I mean, this question of first oscillation maximum, in principle, since this is an experiment still in the R&D stage, in principle, it should be very easy for the beam guys to tune the beam simulation in such a way that the 360 option then sits on the first oscillation maximum.
Okay.
So they probably have to just reduce the energy of the beam slightly, and then you have the first oscillation maximum, or no, maybe you increase the beam energy, and you increase the beam energy, and then you go to the first oscillation maximum.
Okay, the other
That
is
study
just
has still not been done.
yeah. The other is just a short remark that with a 500 kiloton water Cherenkov and with 8-inch photomultiplier tubes, you would really require a humongous number of phototubes. Is that right?
Well, I am not at all an expert in the
Because the
hardware.
area is about 8 times less, and you still have about 30% coverage.
Yeah,
Which is
so
quite significant.
the detector R&D also is underway. My understanding is that not so much has been. I mean, the beam guys have been actually working a lot, and I am aware of very large number of beam options that ESS NUSB has. I am not so much aware of the R&D in the detector simulations yet. What I understand is that they are going to start concentrating on the detector R&D next. So even in fact, the resolution functions that we use at this moment for analysis of ESS NUSB are the ones that was available to us at the time of Memphis, which was like ages ago. So yeah, there is a lot of work remaining to be done in this experiment.
So we are really running late. I'll have just last two quick questions. I think one comment that was left by Sanjeev, and then a question by Bindu. Sanjeev, you want to make your comment?
Yeah, so this is regarding the question you asked. So JSNS2 will have much better electron and pi naught separation and electron and gamma separation compared to mini boon, what they had, and definitely LSND. So since we agree that there must be something going on over there, when we say that we have identified electrons, they can be photons, they can be pi naughts. So because the improvement and understanding they have from T2K experiment. So this is their claim that they will do better in that area, in that area.
Bindu, you can ask your question also.
Yeah, I have a question and a comment. I'll just ask the question first. The question is that you were talking about decoherence effects in neutrino experiments, but you didn't explain them in your slides. Can you just tell us a little bit about the decoherence effects?
Yeah, I mean, decoherence. I mean, there's if you want to know about what is the theory that could lead to decoherence, so essentially.
Well, we have our own thing, but so I want to know your point. Yeah.
So the way I see it is that, I mean, I have never come across any good theoretical motivation for presence of decoherence in neutrino oscillations. I would say that one could still, I mean, it's the same for neutrino decay. I mean, there is no good, I mean, neutrino decay is better than neutrino decoherence. So there is no good theoretical setup for us to believe that that there could be terms in the neutrino evolution equation that could lead to decoherence of decoherence as the neutrinos are propagating. So essentially, I mean, neutrino oscillations is a coherence effect between the different neutrino states.
Yeah.
And if you have a term, it's like a, what's it called? What's it called?
If you consider the wave packet, if you consider a wave packet picture of neutrinos, then which T2K examined in detail, actually you do, I mean, you should get decoherence if you have wave packet pictures of neutrinos, but T2K examined it in detail and didn't get it, but Joule might do something. So there
Yeah,
are
we have limits. We have
Yeah.
limits on the
because
extent
of
of
the wave
decoing is
packet theory.
possible.
I think
We
can
have also from the long baseline experiments also.
And the comment I have is that
I think we should stop. The people, our earlier speakers who we want to thank, who are actually
Okay.
about to leave. So
Okay.
already half an hour beyond time. I think we can have other discussions later on. So sorry about that to cut this thing short, but I think I suggest that everyone unmute themselves and just give a round of applause for all the three speakers of the evening.
Further discussion can be in Slack.
Yeah, so please go to Slack and we'll be very happy to continue the discussion. Okay, so unless the organizers have anything to announce, we can stop the session.
Yeah, so thanks all the speakers for very nice talks, and thanks Amol for chairing the session, and thanks to all the participants to stay too late with us. So thank you very much.
Okay, bye-bye, thank you.
Bye.
Bye.
Bye.